Hello students, this is Dr. Jyoti Agrawal. In the last lecture we had discussed about norm of a vector. Today we will discuss about orthogonal and orthogonal vectors. So how to define orthogonality? So let x be a vector and its length is 1, then we can say that norm of x equals to 1. In other words, we can say that if norm of x equals to 1, then square root of inner product of x and x equals to 1, which implies that inner product of x and x equals to 1, which is a unit vector. In general, if inner product of two vectors x and y equals to norm of x, norm of y into cos theta, where theta is the angle between x and y. So we can say that if theta equals to 90 degree, that is two vectors are orthogonal, then we can say that inner product of xy equals to 0. In other words, we can say that if the inner product of two vectors equals to 0, then those vectors are said to be orthogonal vectors. हम ऐसा बोल सकते हैं कि किन्हीं भी दो वेक्टर्स का इनर प्रोडक्ट कैसे डिफाइन करते हैं, जस्ट लाइक डॉट प्रोडक्ट ऑफ टू वेक्टर्स, एंड इफ द एंगल बिटवीन दोज टू वेक्टर्स 90 डिग्री, देन दोज वेक्टर्स आर सेड टू बी ऑर्थोगोनल वेक्टर्स. नाउ लेट्स मूव टू द नेक्स्ट स्लाइड. Now how to define a orthogonal set? So let S equals to x1, x2, x3 and so on xn be a set where xi belongs to V, be a set of vectors of V. Now here S is a set of vectors of V, then this set is said to be orthogonal if the inner product of any two vectors of it equals to 0, that is inner product of xi and xj equals to 0 if I not equals to j. Also this set is said to be orthonormal set if inner product of xi, xa, xj equals to 0 if I not equals to j, and this will be 1 if I equals to j. So if this condition hold, then this set is said to be orthonormal set. Otherwise, if any two vectors of it equals to 0, then this set is said to be orthogonal set. So in this way we can define the orthogonality and orthonormality of a set. If x and y are orthogonal vectors, then we can prove that a Pythagoras theorem, which is norm of x plus y ka whole square equals to norm of x chi square plus norm of y chi square. This is very important. This is known as Pythagoras theorem. Now how to prove it? First of all, take its left hand side, which is norm of x plus y ka whole square. Now by the definition of norm, we can write it as inner product of x plus y and x plus y. Now here we use the properties of inner product, which are inner product of x plus y and x plus y. We can write it as inner product of xx plus inner product of xy plus inner product of yx plus inner product of yy. Now here inner product of x and x becomes norm of x chi square and inner product of y and y becomes norm of y chi square. Here inner product of xy plus inner product of yx cancel each other because they are complex conjugate. Okay, now let's move to the next slide. Now what is the parallelogram law? We also prove the parallelogram law, which states as norm of x plus y ka whole square plus norm of x minus y ka whole square equals to 2 into norm of x chi square plus norm of y chi square. So take first norm of x plus y ka whole square. Now by using the definition, we can write it as like this one. Similarly, norm of x minus y ka whole square equals to inner product of xx plus inner product of x minus y plus inner product of minus yx plus inner product of minus y minus y. So inner product of x minus y norm of x minus y का whole square becomes equation number second. Now from equation first and second, if we add these two equations, then we get norm of x plus y का whole square plus norm of x minus y का whole square equals to twice of inner product of x and x plus inner product of y and y. So we get 2 into norm of x का square plus norm of y का square. So let's move to the next slide. Okay, now here S equals to V1, V2, V3 and so on Vn be a orthogonal set. Let S be any orthogonal set. Then we know that any two vectors of a orthogonal set, norm and inner product of any two vectors equals to 0. So if y belongs to span of S, then y can be written as a1 v1 plus a2 v2 and so on plus an vn, because y belongs to span of S where ai belongs to f. Then if we take inner product of y with any vector of S, then we get inner product of summation j1 to n aj vj. Now applying the property of inner product, summation j equals to 1 to n aj inner product of vj vi. If I not equals to j, then inner product of vi vj equals to 0 by the definition of orthogonal set. So if I equals to j, now if we take I equals to j, then inner product of y and vi, we get ai inner product of vi. So we get ai equals to inner product of y with vi upon norm of vi का whole square. So we can write any vector y which belongs to span of S as summation I 1 to n inner product of y and vi upon inner product of vi, that is norm of vi का square, then and vi which is equals to summation I 1 to n inner product of y and vi into vi. This becomes 1 if the set is orthonormal. Let's move to the next slide. Now orthogonal sets are linearly independent. We know that orthogonal sets are linearly independent. So a1 v1 plus a2 v2 plus an vn equals to 0. And here earlier we proved that y equals to this one. Now if we put it in this one, then we get I equals to 0 for all I. Thank you students. Next topic we will discuss in the next lecture. Thank you.